First overtime in Super Bowl, and the largest came back ever in playoff, right? So, and it's even better when I'm New England fan. Okay, that being said, let's continue with what we're doing here. Okay. So we talk about intersection is where, division is what we spent quite some time discussing last lecture. So just quickly, a quick recap what division is about, right? So when you do A divided by B, there are two things that you need to check out first. When you do A divided by B, right? There are two things you want to check out first. One is the schema of B must be part of the schema of A, meaning all attributes in B must have appeared in the attributes of A. Otherwise, this doesn't even make sense. Because you're trying to find all the x such that x and y, for any y from B, when you pair them together, they appear as a record in A. What that means is, because x and y together is part of A, and y is from B, is a record in B, which implies the schema of B must be part of the schema of A, right? And that's the first observation, right? Okay. The second observation is, if you look at the output of A divided by B, because the output is all such x values, such that for any y, any record in B, x and y together as a pair is a record in A, and you're printing out all such x values. So the schema of the output is what? Is all attributes in A but not in B. Right? It's all attributes of A except those in the schema of B. Okay? In the schema. So those are the two observations. And then the semantic of A divided by B, meaning the instance of the output, essentially represent all those x values in A that pair up with every single record in B. For example, A divided by B1 gives you all student number who work on product 2. And A divided by B2 gives you all student number who work on both product 2 and product 4. And A divided by B3 gives you all student numbers who work on product 1, 2, and 4. Okay? And the other implication from our discussion in last lecture is you should never construct your query by example. You should never construct your query by example by looking at a particular instance. For example, all of these three queries at the end of the day is simply written as A divided by B. I'm simply supplying different instances of B to get different output. But I never need to change my query, right? I never need to change my query. I'm simply supplying different instances to this query, A divided by B. I substitute B with B1, B2, B3, or B whatever. As long as it's a valid schema, a valid instance from the schema of B, I can execute this query and get all the students who work on every product from B. Doesn't matter if B has 1 product or 2 or 4 or 5 or 6, right? This is not true using the alternative approach I demonstrated in last lecture, using the selection and the intersection approach, right? In that case, you have to change your query whenever the instance of B has changed, which is not a good approach, right? Because your query becomes invalidated as soon as you update the instance for one of the inputs to your query. Whereas in this case, your query stays at the valid query expression, no matter how the instance of the input might have changed. Okay? So that's another key observation we can make from this example. Okay? Expressing A divided B using basic operators, I went over this last lecture. I'm not going to repeat myself. If you don't fully understand what's going on here, you should try to review this and work out this expression step by step, like I did towards the end of last lecture. What you simply do is take an instance of A, take an instance of B, and work out these steps one by one to understand what's going on. Essentially, this gives you all the possible pairs between all such x values and every y value in B. But not all such pairs will exist in A, so you subtract away the instance of A from all possible combinations. What's left after this subtraction is those pairs do not belong to the original instance of A, which means you find at least one y value from B that those x match up with those y and do not appear in A. And that's obviously what we call those disqualified x values. Then you use all the x values from A minus away those disqualified x values, you get what you want. So that's essentially the logic behind this approach. So that's all we need to know about relational algebra. I will use the remaining 10-20 minutes for the discussion of relational algebra to go over some examples, to go over some query examples. And then we will move on to the discussion on SQL. Okay? Once you fully understand what's going on with relational algebra, it becomes extremely easy for you to understand structured query language SQL. Okay? So again, I'm going to use these examples, reserves, sailors, and boats. And these are the instances to my examples. Keep in mind, as I mentioned just now, these instances are really there to help you understand what's going on behind a particular query expression. By no means you want to construct your query using a particular instance. That's always wrong. That's not the right approach. For example, give you an example. If you want to find a sailor whose age above 35, who's older than 35 years old, the right way of expressing this query is, the right approach is this, is select age greater than 35 on sailors. Right? It works for this instance, it works for any valid instance of the sailor's schema. You may argue, okay, looking at this instance, what about I express this query using the following approach? Okay? Is this a valid approach? Is this a valid approach? Well, with respect to this particular instance, it is a valid approach for the query of finding all sailors older than 35 years old. But in general, this is the wrong approach, right? Because what if I insert another sailor, sailor ID whatever, age 48? Then this query is no longer right. Does that make sense? In the same spirit, this is wrong as well. You cannot say what about this approach? Well, again, it's wrong, right? With respect to this particular instance, it is correct. But overall, your query expression should work for any valid instance of your schema. So this is wrong as well. I may insert another sailor record who is not captured by your existing selection condition, and it's wrong. Whereas if you think about this approach, it works for any valid instance of the Sailor's table. So that's the requirement. Okay, question over there?
Does the caret mean and? The little caret?
Yeah, that represents and.
Okay.
Okay, so this is important to remember, right? So I could actually give you these examples without providing any instances. So I can hide those instances and ask you to do all the queries I'm gonna show you in the next few slides. But I'm providing these instances to just help you understand what's going on, rather than as a way to writing your query. So the same argument goes towards you problem 1 in your homework 2. Actually, one of you asked a question on Canvas. Is credit card refers to the set of Visa, MasterCard, American Express, and what's that, Discovery card? The answer is no, right? So that particular instance in problem 2 has only those 4 credit cards. But I could easily change the instance of that database so that there could be more credit cards in my database, or I could delete one of those from existing list of credit cards. In other words, you should not construct your query based on one particular instance of any table. Right? You should construct your query based on the general semantic of your schemas, rather than a specific instance of any schema. Okay? So that being said, let's move on to see a few examples. The way I'm going to do this, I'm going to start with really easy, simple ones to just get a feeling of how this works. Then we move on to a little bit more involved examples. Okay? So the first one is find name of sailors who have reserved boat 1 and 3. This is fairly straightforward. First of all, you notice that the names attribute for sailors, the name attribute is not available in the reserve table. If your goal is to find sailor ID who have reserved boat 1 or 3, you can do that using reserve table alone. Right? You don't have to use any other table. What you do is, if your goal is to just find the sailor ID who have reserved boat 1 or 3, all you need to do is from reserves, then you put out those sailor IDs. Okay, fairly simple. But the question here asks you to find the names of those sailors, which is not available in the reserve table. So what you have to do is do a join between reserve and sailors first, natural join. What this does is match every reserve record with the corresponding sailors record. You can kind of think of this as expanding a reserve record with all the other necessary information about the sailor who has made that reservation in the first place, which of course includes the name and rating and all bunch of other attributes about the sailors. But what we really care is just the sailor name. And then after you do the join, you perform a selection. You only care about those information on boat 1 or 3, then you put out the sailor name at the end of the day. Okay? And I'm going to use this particular example to demonstrate to you that relational algebra is operational. We had a little bit discussion on this issue last lecture. I'm going to re-emphasize this point I'm trying to make. Okay? So this is one approach to this particular query, right? You may immediately make another observation, which is this does not give me a sailor name, but what if I take the output of this, the sailor ID, and then I do a natural join with sailors. So what is the schema here? What is the schema for this relation here? The schema here is only SID, right? Because I do the production end. And what is the common attribute between this and sailors? Well, that's just SID. Does that make sense? So who will survive this natural join? Only those sailors who have actually reserved a boat 103 will survive this natural join, because only those sailor IDs will show up in the list of this table right here. And then finally, I can do a projection at the end. Okay? And if you compare this approach against the approach presented on this particular slide, they deliver what you want. Right? The what is the same, actually. What here is the same as what in the slides. But how you do it is different. In the first approach presented from this particular slide, you do the natural join first, then you do the selection, then you do the projection. Whereas in the second approach, you do the selection first, then you do the projection, then you do the natural join, and then you do another projection. Which is more efficient, generally speaking?
The one on the board.
Can you explain why?
Well, because you limit your schema down to a smaller
Not limiting your schema, limiting your instance. Right?
instance, yeah.
Schema does not change after the selection. But actually, this step does limiting schema as well, in a sense, right? Because it projects down to just one attribute. So if you think about this approach, what happens is you narrow down your instance to a smaller subset. Assuming you have hundreds of votes, this narrow down to only those records concerning vote 103. Then this further narrow down to only SAIL ID from those smaller subset of records on reserve. So at the end of it, this leads to a very small instance to be natural joined with sailors. That obviously is much more efficient than take a huge reserve table and natural join with sailors, and then only do the selection afterwards. Right? So clearly, the second approach is much more efficient. Okay? And this illustrates the point I was trying to make earlier, which is relational algebra is operational. Using the same language, relational algebra, we can not only express what we want, but also how we want to do it. And that's why relational algebra is the language used by the relational engine inside the kernel to represent your query. So the first step happen inside a relational database engine is to take a SQL query as input and convert that into a relational algebra representation. And then using that relational algebra representation, I can morph the same relational query into different representations, like either this or this, and try to figure out which is more efficient. And then I will stick with the what we call the query plan that's more efficient to do the actual execution of the query. Okay? So that's essentially the pipeline. So that's solution one. Oh, the animation kind of messed up a little bit. Anyway, I will fix this afterwards. So let's move on to the second example. Find name of sailor who have reserved a red vote. Find the name of sailor who reserved a red vote. Let's go back to the instance here. Okay. Find the sailor who reserved a red vote. How do you do that? Well, again, there are multiple ways of doing this. One approach is to make the following observations. First of all, you still need the name of sailors, meaning you do need a natural join between reserve and sailors so that you can quote-unquote expand all the reservation record with the information on the corresponding sailors. So you do need a natural join between reserve and sailors for that purpose, because you want sailor name at the end of the day. Observation number one. Observation number two, red color boat. The information about the color of the boat is not available in the reserve table, rather it is available in the votes table. So you not only need to expand reserve towards the sailor's end, so that you can have sailor's information attached to a reservation record. You also need to expand the reserve record to the boat direction, so that every reservation record comes with the information on the boat as well. Does that make sense? Which means you do need a natural join between reserve and sailors. You also need a natural join between reserve and boat. And you can simply express that as, so I'm going to simplify my writing. R stands for reserve, S stands for sailors, B stands for boat. Okay? So So you simply do this. And this natural join will automatically happen on equality condition on CIDs. And this natural join will automatically happen on equality condition on both ID. Because the common attribute between these two is both ID. And the common attribute between this is CID. Does that make sense? And then you basically say, okay, at element 1, select color equal to red. Okay? Those are the expanded reservation record concerning red color boat. Now using the expanded reservation record, I can now print out serial name. Right? Does that make sense?
Is that natural join associative? Does it matter which join?
Good question. That's an excellent question. That's actually the next point I will try to come to. The question was, what's the order? I think what you're saying is, what's the order of executing a natural join when I write two natural join in a row like that? Okay. It's left to right, which means you will evaluate this first. Here comes an interesting observation, right? We know the natural join between this, if I write it like that, then I know the natural join here is CID equal to CID, intuitively. But since I do not have this bracket, this natural join actually is between this with S. This, what's the schema of B join S, or B join R? What's the schema of this? I'm not asking the instant, right? I'm just asking the schema of this. Okay, let's do it. BID, both name, color, and do you want, you obviously need CID. So these are from B, and this is from R. But you will ignore the second BID because for common attributes in natural join, you only keep one copy of the same attributes. So you will not have that BID on reserve, you would have date information. Right? So that's the schema of, right? And you take this natural join with S, what are the common attributes of the two? They're still just SID. So this join still happens between SID. But between this schema and S. Does that make sense? So obviously this is not necessarily the most efficient approach to this query, right? To find the sailors who reserve red color boats. What you can do, obviously, is narrow down the boats instance to only red color boats. Then you natural join reserve, natural join sailor cordell, sailor them. You can do even better. Notice that after you have narrowed down to the red color boats, the other attributes about the boat, such as name and even the color itself, is irrelevant anymore. All I care after this point is just the boat ID. Right? Once I know I'm dealing with red color boat, from that point onwards, the color of the boat, the making of the boat, the price, imagine if you have those additional attributes, it's totally irrelevant. All you care is just the boat ID, so you put out the boat ID. Okay? Then you naturally join with reserve. And after you have done this natural join with reserve, even the boat ID is irrelevant anymore. All you care is just the sailor ID. Because now it gave you the list of sailor IDs who have reserved a red color boat. And then I only use this sailor IDs natural join with sailors. This is a much more efficient way of doing the same query, right? That being said, for your homework too, and for this class in general, right, we do not penalize you for writing an inefficient query, because the focus here is really to understand the semantic relation algebra and SQL as well. We encourage you to explore more efficient expression of your query, but we will not penalize you for that. Meaning, among these two solutions, both are okay. Yeah.
When you're doing a natural join, is it good practice to just make it the first part of the natural join as like small as possible? Because like you're making the precision here very small, and then natural join it. So would it be better to do that on a common basis?
In general, yes, of course. From an efficient standpoint of view, not only you want to make the first relation as small as possible, you want to do that on both relations. Of course, you want to do so without impacting the correctness of your work. Huh? That make sense? For example, it makes sense to, in this case, to project out the seed ID after you have done this join. But it doesn't make sense to somehow narrow down the sealer table before this natural join, because you don't know which sealer will end up joining with a record on the other end. So there's nothing you can narrow down using a selection operator, but actually you can narrow down this by you can actually further narrow down the sealer table by projecting on sealer ID and sealer name, because at this point, for the purpose of this course, all you care is sealer ID so that you can do the join, and sealer name so that you can do the projection in the end. You do not care about sealer name and sealer ratings. So this actually can be a little bit more efficient. Find the sailors who reserve a red or green boat. Okay, so it's a little bit more complex than the last one. So what you do is you use a renaming operator now. Okay. So renaming operator, quick recap what renaming operator does is the quick letter rho followed by the name of the output schema that you want to rename into. Right? Followed by the attributes to rename, if any. Right? You don't have to rename any attributes if you don't want to. Followed by your relational algebra group. Okay? So that's the general convention of the renaming operator that we have discussed. So in this particular example, my relational algebra query is color equal to red or color equal to green from both. Then I'm going to rename that called the output temp boat. So now whenever I refer to temp boat, I refer to that instance, which is a subset of boats that contain either red or green color boats. Okay? And in this particular example, I'm only renaming the name of the output schema. I'm not renaming any of the attributes. So the attributes of temp boats are still the same as the original boat schema, which are boat ID, boat name, and color. Because I'm not renaming any of the attributes, I'm just renaming the output schema itself. Okay? Now I use this temp boat and apply essentially the same thing here. Because now instead of red color boat, I have red or green boat. I can do it. Okay? Same logic. Okay? Next, excuse me, next example. Very simple. I change this all to and. We reserve both a red color boat and a green color boat. Can I simply change this to and? Meaning, I change this all operator to an and operator. Does it work? You said no. Why?
Because I would be looking for both that are red and green. Right?
And there are no such both, right? Yeah, excellent. Okay, so you cannot simply change this all to and operator to capture this group, right? Any suggestion as how we might be able to do this? without, of course, without jumping ahead on the slides on your screen. Okay.
Could you just do a natural join between the sailors who have reserved red ones and the sailors who have reserved green?
Okay, what you're saying is, what she is proposing is that I do this for the red color boat, then I do this for the green color boat. For the result, I'm gonna natural join them somehow, right?
And, yeah, and then take out the unwanted bits that
Yeah.
aren't the same.
So one thing you have to be a little bit careful is you don't want to do the final natural join on sailor name, because name may be a duplicate referring to different sailors. So what you want to do is put our sailor ID in this step right here. This gives you a list of sailor IDs who have reserved red color boat. Actually, you can do it here using this output without natural joining with sailor first. That gives you a list of sailor IDs reserved red color boats. Then you do the same thing to find the list of sailor IDs who have reserved a green color boat. Now you can either do a natural join to find the matching sailor IDs, which means a sailor ID value has appeared in both lists. That implies this sailor has reserved a red and a green boat. Or you can use intersection to do the same thing. And then using the final list of sailor IDs after that step, natural join of sailor to find their names. Okay, so that's essentially the approach to this query, right? So to simplify your writing, you can use renaming operator to find temp red and temp green. This gives you a list of sailor IDs who have reserved a red color or green color boat respectively. Then you intersect them or natural join. You can actually, in this particular example, intersection and natural join does the same thing. Then you finally join with sailors to find the name of those sailors who reserve red and green boats. Okay? Now moving on to the division example. Find the names of sailors who have reserved all boats. So let's come back to the schema and instance here. How do I find sailors reserve all boats? Obviously, I will need to use the reserve table. And this is a good example for you to use division, right? It's very similar in spirit to the division example we illustrated. Find student numbers who work on all projects. Find sailors who reserve all boats. It's essentially the same thing, right? So the first attempt, some of you might argue, okay, this is same to that example, right? So I can just do reserve divided by boat on that. So every boat must pair with some reserve record for that reserve to survive. So that means you have reserved all boats. Is that right or wrong? Is this expression here doing what we want to do? Find sailor IDs. Let's say my objective is find there might be more than one such sailor. Huh? Find sailor IDs who have reserved all boats. Is this doing this? Can someone argue this for me? Yes or no?
No.
No? Okay. All right. First of all, let me write down your answer. Why?
Both had columns that don't exist in reserve, so the division won't even work.
Okay. Excellent. So that's the first observation, right? Remember, that's essentially the first thing I said to kick off today's lecture, right? In order for you to do A divided by B, what's the requirement? The schema of B must be part of the schema of A. Is that the case here? This is your A, this is your B. Obviously, no. There are attributes in both that do not even belong to reserve table. how can a reserve record match up with every boat record and still be part of reserve? That's impossible. How can you have anything here that match with a boat record and still belong to reserve? That's impossible when you have attributes of boats that doesn't even belong to reserve. The boat name is not even part of this. Anything match up with a boat record obviously cannot belong to the reserve schema in the first place. Does that make sense? So that's the first observation. Does that make sense? All of you? So how do you fix that? What you care is, yeah, go ahead.
Me?
The guy behind you.
You can project for both ID and those.
Excellent. You can put that out. Because all you care is the list of boat IDs to uniquely identify all the boats. You don't care about the color, the name of the boat. Does that make sense? Now this is, I define this as B prime, the new B prime. Now this B prime, the schema of this is simply BID, is part of the schema of A. Does that make sense? So at least that passed the first sanity check. This is what we call sanity check. Right? Before you even check the semantic of your query, you need to make sure it's syntactically correct. Right? So at least now it's satisfied the division requirement that the schema of B is part of the schema of A. Now let me ask a follow-up question then. Does this now give what you want?
No.
Jared?
No, because now you're actually going to get all kinds of reserve, not necessarily the same sailor.
So let me ask you this question though. What's the output schema in this case? Can you just tell me what's the output schema when you write a query like this? Like reserve divided by projection of both IDs. What's the output schema?
SID and day.
SID
And day.
and day. Okay. Why the output schema is SID and day?
Oh, because you take the column from both that you're using and you take that out of the schema.
So what's A divided by B? Equal to all such x such that for any y from B. So y, obviously, this means y must be a record of B. There exists x and y from A. Period. So what's the schema of x? X and y together is A, and y is from B. So x must be those attributes in A, but not in B. And that's exactly what we have here. That's x. That's your x. All the attributes in A, which is sailor ID, day, and boat ID, right? If x and y is from A, when y is boat ID, x must just be sailor ID and day. Okay? That's essentially the second point I mentioned at the beginning of today's lecture. Right? The output schema is whatever in A, but not in B. Schema-wise, okay? Not instance-wise. So that's the output schema. Now that being said, can you further tell us whether this query does what we want?
It won't do what you want because it'll only get you the SIDs of sailors who reserved all the boats on the same day.
Excellent. What it does actually is, if you think about the semantic of this, it finds all such x that match with all the y. All the y means all the boats. So you're finding all such x which match with all the boats. What that tells you is you're finding all the sailors who reserve all the boats, yes, but restricted to that all these reservations must happen on the same day. So you are really finding a subset of what you want. Yes, these are the sailors who reserve all the boats, but on the same day. That could be too restrictive. That's not what the query wants. Right? The query asks you to find the sailor who reserve all the boats. Doesn't matter whether those reservations happen on the same day or different days. So how do you fix this? How do you fix this? Well, get rid of
The day
the
column.
effect of date. Get rid of the impact of date. Which means you put that off serial ID and boat ID. Now this shows you who reserved which boat, regardless of what date that reservation happens. Divide by all the boat ID. Now this, the new schema of A now is SID and boat ID. Whereas the B schema is boat ID, so the output schema is simply SID. By our discussion so far. Which means for every boat, for any boat ID, this SID has matched up with that boat ID in the original schema, which implies he or she must have reserved all the boats. Okay? So it's a very subtle example, but this illustrates to you relational algebra queries, and later in SQL, it appears to be very simple, very intuitive, but it actually can get really, really tricky to write, to get it right. It's not as easy as it may sound. Okay? Some things are hard to do, right? Once I tell you something, you know that's hard to do. For example, down 25 points by 1/4 left, come back and win the game. That's hard, right? But sometimes it sounds easy, like get 3 more points, win the game. But it's really hard to do. That's what Falcon needs to do. If they kick that field goal, they won the game. Fairly easy thing to do, right? Sounds like really easy thing to do, but sometimes seemingly a very easy thing to do turn out to be a really, really hard thing to do. Right? So this is the point I'm trying to make here. All right. Okay. What about I move on along this direction? Say find the names of. Okay. By the way, this gives you only the sailor IDs who reserve all the boats. What about sailor names? That's easy, right? You take the output of this whole thing. And you match it all with sailors in the end. Then you product out the sailor name. Right? That's essentially what I'm doing on the slide using two-step approach, using the renaming algorithm. Essentially the same thing. Okay? Now, what about find the sailor who reserve all interlake boats? Interlake is a name, right? You could have multiple such boats named as interlake. Okay, that makes sense. Here, I'm gonna emphasize again. Do not write the query by example. For example, if this is your input query, right? You look at the instance, which is given here. Oh, you say, okay, that's easy, right? I find there are 2 interlake boats. Then all I need to do is find reserve. I do a selection on boat 101 and boat 102. That's wrong, right? Because what if I insert another boat called interlake later on? Or I delete one of the interlake boats? Then you query by example, query by instance construction is wrong. Okay? That's another case where I want to show you never construct your query based on specific instances of your input. So find the sailor who reserve all interlake boats. You know, everything stays the same except that you want to, before you product out the boat ID, you want to do a selection using the interlake condition. That's all. The rest stay exactly the same. Now, moving on to a little bit more trickier example. Okay? So for each boat, so I'm going to use a somewhat artificial example because typically you do not do this, but then I'm going to use this to motivate a more realistic example for the next slide. Then I will conclude the discussion on relational algebra. So this is a somewhat artificial example, right? So people in practice typically do not do query like this. But for the argument's sake, let's start with this one. For each boat, find the sailor with the smallest sailor ID who has reserved this boat. Typically, you don't do this. Why you care who had the smallest seed ID among all the seeders reserved this particular boat? But I'm going to use this to bring out a bigger point I try to demonstrate in the next slide. So how do you do this? This sounds like very, very hard work to do, right? Because you need to do this for each boat when you don't even know how many boats you have in your instance. Could be 10 boats, could be 100 boats, could be 1,000 boats. And that's point number one. Point number two. And you want to do this for each boat, and there's no such thing called for each. There's no for loop in relational algebra, right? You cannot say for boat ID equal to 1 until 1,000 do this. There's no for loop in relational algebra. Challenge number one. Challenge number two. There's no aggregation operator like min or max in relational algebra. Right? Is that right? We never learned something like min or max in relational algebra. Right? How do you find the smallest seed ID when you do not have aggregation operator like min or max? So here we're going to use a particular instruction called self-join. So what you do is you take an instance and join with itself. Join with no other but itself. That's a self-join. And you may wonder why on earth you want to do a self-join. You want to do that in cases like this, when you want to compare records from the same instance in a pairwise setting. In other words, if you think about how we're gonna approach solving this problem, it's the following. Okay, for each boat, from the reservation table. Okay, if a boat never appeared in the reservation table, I don't even care about that boat, because there's no sailor ID ever reserved that boat, right? So here, first of all, I limit myself to boats who ever appear in the reservation table, in the reserve table. So for each boat ID in the reserve table, how do I find a smaller sailor ID? I don't know how to do that, but I know for sure I can find sailor ID who reserved that boat that's larger than some other sailor ID. If I do a self-join, I compare every two pairs of such record. Meaning I take boat ID, sailor ID from one record and compare against all the other records on the same boat ID, where boat ID equals, but sailor ID is not equal. That means one of them is larger than the other one. Does that make sense? And the one record who is never greater than any other record must be the one with smallest sailor ID. Does that make sense? Essentially bubble sort. I check one record against all the other ones. If you never become greater than any other one, you must be the smallest one. Does that make sense? But this checking requires checking record against the set itself. That's a join operation. And in particular, that's a self-join. So how do we do this? Well, first of all, I take the reserve table. I don't care about the date of the reservation, so I project away the dates. I project out seed ID and boat ID. I rename this as R1, SID1, and BID1. Then I do the same, but now I rename this R2. So I got two copies of the same instance. I rename them differently. Does that make sense? So far, it's easy, right? That's very easy. You are getting nothing but two identical copies of the same instance from the reserve by projecting away the date of the reservation. You don't care about that. So far, so good? And then you do a self-join between R1 and R2. Why I call that self-join? Because they are essentially the same instance. It's just two identical copies. I join them, and my join condition is boat ID equal to boat ID. And seed ID 1 greater than seed ID 2. So essentially what I'm doing is, from the cross product, remember, natural join, sorry, this is natural join, this is a theta join, a condition join, right? The first step in condition join is to produce the cross product of the two input relational instances. The cross product between R1 and R2, what do they do for you? It gives you all the possible pairs among this instance itself. Right? That's what it is. And among those pairs, I only care about what? I only care about those pairs referring to the same boat. But I do this for each boat. The for each semantic is automatically captured by the semantic of natural join, because natural join, semantic of condition join. Semantic of condition join is for each record in the cross product, you check the selection condition. That's where the for each logic is captured. So you loop through every record in the cross product. Whenever you find a pair talking about the same boat, you check if theta ID is greater than the other one. This second checking is needed, because there are cases where it's a self-join, right? There are cases where both ID are the same and theta ID are the same as well. You pair against yourself and show up in the cross product. That's possible. And that's not what we want. We want to get rid of those ones. And then you finally put that out. It's very important which one you put that out. So in the cross product, what do you have? You have theta ID 1, both ID 1, theta ID 2, and both ID 2. Okay? Now, if my original instance is okay, suppose that's my original instance. What the cross product will look like? Running out of space, but you got my point, right? So this is a simple example of that. Okay? That make sense?
Can you move the chair? The chair.
And,
The chairs. Can't see it.
The chair's in the way.
The chair with your coat draped over it.
okay.
Yeah.
So, blocking view. All right, so now you loop through this and check the condition. First of all, both ID must match, which means this one, this, you don't even consider this. You don't even consider this. You do consider this. You don't even consider this. You consider this. You don't even consider this. You do consider this. Okay? That's the first one. And theta ID 1 greater than theta ID 2. Nope. So this is eliminated. Theta ID 1 greater than theta ID 2. No. Eliminated. No.
Yeah.
Yes. And no. Right? So this survive. Does that make sense? And this is eliminated too. Right? Because theta ID 1 is not greater than theta ID 2. Okay? And then you put that out. Theta ID 1 and theta both ID 1. which means what you are projecting out. For each boat, you are projecting out the guys who have reserved this boat with a sail ID who is greater than some other one. Does that make sense? And the output in this case will be just 2 and 8. Let me finish my example, I'll take you. Okay? That's the output, right? Does that make sense? This means for each boat, the output here contains all the sailors who have reserved this boat with a bigger, larger SID value than some other sailor. I don't know what some other sailor is, but I know you're definitely have a sailor ID larger than at least one other sailor. Now you see the trick. I take all the sailor ID and boat ID from the original instance, subtract away those guys. Whatever left must be, for each sailor, for each boat, the smallest sailor reserving that boat. In this case, you take this whole thing minus away this. That's your final answer. Does that make sense? All right. Now I can answer your question.
So to get that, you would just subtract what we just made and then, well, is this final one on the board?
Oh, sorry. The final one I didn't show you.
That's like,
It's like right before the overtime, I know you're not gonna win no matter what. It just confirmed what I believe. You know, but seriously, by that point, the Falcons is like they're just not there anymore. Right? They're just ready to give the game away. Okay? Of course, it's easy to say that. If you ask me to bet $1 million in Las Vegas before that overtime kickout, I still won't bet it. Okay? Alright, so it's always easy said than done, I guess. All right. Okay. So you may argue, okay, interesting, but why you want to do this? Who cares? Like, who want to find boats reserved by some guy with a smaller CID? Doesn't matter, right? But this makes sense now. For each boat, find the sailor with the largest rating who has reserved this boat. You do care about, if you're owner of Sailors Club, you do care about this. Oh, why you care about this? For example, you want to do some analytics. Whether skillful sailors have certain preference on certain boats. Right? Maybe that's why they got a better rating. Because they learn the secret of different boats. They always reserve the good boats. That gives them an edge in the competition. And you want to do this kind of analytics. You want to see whether there is any correlation between boats and highest rated sailors. Reserving them. Does that make sense? Right? The first step to do analytics like that is to do exactly this query. And how do you do this? Well, exactly same logic as what I have done here, except that you do this over ratings. But you also need to carry the sailor ID along the way, because ratings is not unique enough to identify a record. So you need to use both sailor ID and rating, but do this comparison on ratings. So specifically, you do a natural join between reserve and sailor, and put out boat ID, sailor ID, and rating. In this case, I do need to qualify the sailor ID with sailor.sailor ID, or reserve sailor ID. Doesn't matter because it's natural join. But you need to specify which sailor ID you are projecting out. You don't have to do this for BID and rating because there's only one appearance of those attributes in the output schema, so there's no ambiguity whatsoever, even if you don't qualify that with the name of the schema. Does that make sense? And you do the same for the same query again. Then you do a subjoin of the two, where the condition is boat ID must be the same and sailor ID must be different. You're talking about different sailors on the same boat, so both sailors have reserved the same boat, and one has a smaller rating than the other. Now you project out those ones with smaller ratings. not the larger one, because you want to find, your goal is to find the largest ring. Then you use the whole thing, subtract away those with smaller ratings on a particular boat. Whatever left must be the sailor who reserved that boat and with the largest rating. Right? Exactly the same logic as before. That make sense? Yeah.
What if they have the same rating?
What?
What if they have the same rating?
Well, if they have the same rating, they both survive. So they will not satisfy this condition. So nothing will be put out, but that's okay. That means both sailors have the largest rating, and they happen to reserve that boat. Then I have more than one reserving that.
Or both of them have the same rating, but it's not the largest, and they'll both lose some other matchup and be taken out that way.
Yeah. Okay, you can think about this further. If you have questions, we can talk offline. Okay, but the logic is the same as that last example. Okay, that's enough exercise for relational algebra I want to do today. Okay, so let's move on to the next lecture, which is SQL. So for this discussion, I have set up two database servers that later I will show you the details how to connect to the database servers on Canvas. One is a MySQL database server. The other is Postgres SQL. Okay? Postgres SQL. Both are open source database systems that are two largest open source database systems are used worldwide for different applications, right? So I'm going to expose you to both database systems in this class. So I set up two servers for you to connect to, and I will show you how to connect after the lecture on Canvas. I will release details how to connect to them on Canvas, so that you can practice the semantics and syntax you will learn from the lecture. And also you will later on be doing your project on one of them. Your project will be done by MySQL. We'll use MySQL for that. A little bit history, MySQL. MySQL was a community effort until it was purchased by Oracle. I think maybe 5 or 6 years ago. So Oracle now owns MySQL. And Oracle released two versions of MySQL. One what they call enterprise version, which is not open source. You have to pay for it. The other version is what they call community version, which is open source. As you can imagine, the enterprise version is much better than the community version because they have to make money. If they make the two versions the same, nobody will purchase the enterprise version. Okay? So that's MySQL. PostgreSQL, on the other hand, is completely free, open source. There's no such thing called enterprise version. There's only one community version. And PostgreSQL was initially built by Michael Stonebaker when he was a professor at Wisconsin, and then moved on to a professor at Berkeley. He was the winner of Turing Award last year, the year before last year. Now it's 2017. So he was a Turing Award winner in 2015 for his contribution, largely for his contribution in building large-scale open source database systems. PostgreSQL being the most representative of his efforts. I encourage you to read his bio and story online. Just Google Michael Stonebaker. So he's a big name in database world. Okay. All right. So SQL stands for Structured Query Language. It is the most widely used relational query language. The current standard is SQL 2011. So what do I mean by SQL standards? So when database system was first designed around 1980s, there were different vendors, right? There were Oracle, there were a couple of other vendors like IBM DB2. And each comes with its own design, and furthermore, each comes with its own language specification. And this creates a chaos for end users. Imagine if you are a developer then, you try to write some application over a database product. If you don't know which database product you're going to end up using, this is a big headache for you development job, right? Because you have to write case statement or if else in your code. If the database is Oracle, I do this. My query is expressed like this. Else, if it's MySQL, my query looks like this. Else, if it's Postgres, my query looks like yet another form. The list goes on and on. You can imagine this is not a good way to write a program. So these database vendors, they realize not only this is bad for developers, this is actually bad for them as a whole in pushing or selling this database market. Right? So they eventually got together and sat down and said, okay, let's try to invent a standard that everybody can agree on. Then we compete on a level field, right? Rather than play by different rules. Okay? So this is what we call industry standard for SQL, for query language. Okay, they meet every few years and improve this standard based on the previous version. The current standard accepted by everyone, by most database vendors, is SQL 2011. Okay. Of course, MySQL, PostgreSQL, and even Oracle SQL Server DB2. In addition to the standard they have agreed to, they have some add-on features that are always specific to their particular database servers that you need to be watch out for. Okay, but the core part of this different database system, they conform to the same standard. Okay, this applies to not only relational database system but also to NoSQL system, as I mentioned at the beginning of the semester. NoSQL stands for not only SQL, right? Like Hive, Hadoop, all these efforts, they started with no support for SQL, and they evolved into what they are today, which is almost all the NoSQL systems have some form of SQL-like support, SQL-like language at the top, right? We'll talk about NoSQL system toward the end of the semester if we have time left then. Okay. So in the quick overview I provided in the discussion of relational model, we mentioned that broadly speaking, you can classify SQL into two categories. One is what we call DDL, the other is DML, data definition language and data manipulation language. And DDL refers to those features in SQL that concern about creating your schema, manipulating your schema, creating instance of your schema in that category, right? So let's start with create table as a concrete example. I'll start with this one. So create table, this keyword is for you to specify the schema. Is for you to specify the schema of your relational database. You supply create table with the name of your table, followed by a list of pairs, where each pair has two components. One is the name of the attribute, the other is the type of the attribute. By the way, this is written using regular expression format. Okay. Curly bracket means a set. Curly bracket means a set. A square bracket means that's optional. That means optional. You can supply or you don't have to supply. Some expression there. Okay. So the way you read this is you're going to have a set of column name and data type. And for each column name and data type, there could be some default expression. There could be a column constraint. Those are optional. That's the way you read this expression. Does that make sense? It's a typical regular expression format. Okay. At the end of that list, you can also have something called table constraint. And what's the difference between column constraint and table constraint, and what are these? I will demonstrate those using concrete examples to follow in the next few slides. A couple words on data types. Data types, of course, vary between different database servers, right? So the data types supported by MySQL will be different from data types supported by PostgreSQL. But for the most part, most database systems have a core set of data types they all support, okay? Which is what we're going to talk about. One is character n, which means a fixed length character string, or fixed length byte array. Why I call a fixed length character array a fixed length byte array? Because each character is a single byte. Does that make sense? Each character is just a single byte. So when I say character, when I say character array, which is char 20, for example, what that gives me is a character array of 20 characters. So that's a string of 20 characters. And it's fixed length, which means regardless of the actual value going into this column will occupy 20 bytes. For example, if you have a name, like that, and you have multiple records, So suppose you name column is Feifei. So that's only 6 characters. And oftentimes in computer systems, a string is end with an end of string character. So in most cases, this is 7 characters. It's translated to 7 characters, right? 6 characters for the string itself with an end of string character attached to it. However, you declare the data type of this as char 20, which means this will still occupy 20 bytes on disk, even though the value itself only occupies 7 bytes. That make sense? So that's fixed length. That's what I mean by fixed length. Whereas the next one called character varying array, in short, oftentimes known as varchar, variable character array. So what's the difference of the two? Well, what this means is you're going to have variable length for each value for this column that goes up to 20 bytes, but each value uses the actual length, actual number of bytes it needs on disk. So what that means is if you use the same value of Feifei for the name, this varchar will use only 7 bytes on disk. If you have another name called, let's say, John Smith. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? 10 characters for the name itself plus 1 character for the end of string. So what happened here is I'm going to still use 20 bytes, but the string itself will occupy 11 bytes. Okay, that's what happened here. If I take the same example here, what happens? Well, this will use only 11 bytes. So on and so forth. Layout on disk, what really happens is, if that's you, I will continue on before taking your question. What that looks like is you're going to have 7 bytes for Feifei, and then follow that is 11 bytes for John Smith. End of string character. End of string character. Whereas in this case, what happens? You're going to have empty space, then another 20 bytes. And so on and so forth. Okay? So that's the difference of the two. And this varchar means you can go up to 20 bytes. You cannot go beyond 20 bytes. Okay? You cannot go beyond it. Question?
So what's the advantage of using a fixed length character of a variable name? Because everything you've said so far is in favor of the variable.
Okay, let me throw that question back to you.
I I would imagine it's probably faster to work with the fixed link because you don't have to look at how big the string is to figure out how much space to use to store it.
Okay, that's a good intuition. What he says is, it's probably faster to work with fixed length string into a query, like look up a particular value, because you know the offset. Regardless of the value, you know each value occupies 20 bytes, so it's very easy for me to jump around to find the data I need. Right? Is that what you're saying?
Yeah.
Whereas in variable length, because each value is different lengths, you imagine you have a long list of these values. To find a particular value, it's really hard to calculate the offset. You cannot immediately jump to any particular value. You have to linear scan through until you find the value. Does that make sense? But it goes both ways. It's a double-edged sword. Right? Fixed length also means that once you find the value, you're reading more data, you're processing more data than necessary. Right? So yes, that's one point. But there's more to it. Along that line, actually a bigger point is this is more frequently towards updates. And see this? If I delete a value, okay? In this case, if I delete John Smith, and later I insert another value into the name field, I can recycle this 20 bytes without adjusting, without making any adjustment to my database. Whereas in this case, if another value follow it, if I delete John Smith, and later on I try to insert another value to this list, I may not be able to recycle this, right? Because unless the next value to insert is exactly 11 bytes, I'm going to either use less than available bytes, or I'm going to need more, which means I have to move all the following values ahead, which is very expensive. Imagine you have a long list. You have to move all of them to make space, to make room for that new value to be inserted. Or you end up with using less number of bytes, so you end up with holes everywhere. Eventually this becomes super bad to maintain. So that's a major reason why people use this. Another point, let me finish, then I'll take your question. Another point is variable length, right? When you design this database, you have to go with maximum possible length. So sorry so a downside. So it seems like you should go with fixed length, right? But another major drawback of fixed length is that you might have to go with the worst case scenario, right? For example, the name distribution of human names. If you look at the human name distribution, this is the length of your name. This is the frequency of a name with that particular length appear. What do you expect this curve to look like? It's more like this, right? Most person's name is about 15 characters, or less than that, 10 to 15 characters long. There are very few people with really long names, but they do have such cases. If you go with fixed length to cater for a value like this, what happens? You have to go with the maximum possible length, which means you end up, this is not what it looks like. What it really looks like is you are using, for the most part, you are using only a small part, and there's only one record you end up using all of it. So that's the trade-off of the two. I stop right here. Thank you.
Yeah, we should, yeah. For the it up with like